Okay, in this lecture we're going to start our section 4.3 material on linearly independent sets and bases. So throughout this section, when we talk about a basis for a vector space, or bases, we're trying to identify and study subsets which would span a vector space or a subspace of a vector space as efficiently as possible. So we're trying to come up with a minimal or the most efficient spanning set of a given space. Now, in order to introduce some of the terminology that we're going to discuss in this section, we need to extend the definition of linear independence that we had considered in Chapter 1 from vectors in Rn to vectors in a general vector space. So the definition is very similar here. We would say that an indexed set of vectors, v1 through vp, in a vector space V, is said to be linearly independent if the vector equation, that is the linear combination c1 v1 plus c2 v2, and so on, up through cp vp, is equal to the zero vector, has only the trivial solution where c1, c2, up through cp, these weights of our linear combination, are all equal to 0. And the set of vectors v1 through vp is linearly dependent if there exist weights c1 through cp, which are not all 0, such that the linear combination of the vectors v1 through vp with those weights is equal to the 0 vector. Now, in this case of linear dependence, this equation is referred to as a linear dependence relation among the vectors v1 through vp. All right. So a little bit about some conventions that we'll use for linear independence of vectors in a vector space. So similar to the conventions that we were using for vectors in Rn, any set which contains a single vector v is considered linearly independent if and only if v is the non-zero vector. So any single vector set is linearly independent as long as that vector is not the 0 vector. Similarly, a set of two vectors is linearly dependent if and only if one of these vectors is a scalar multiple of the other. That is, if the two vectors can be considered parallel or one vector a multiple of the other. So for sets of single vectors or two vectors, it's easy to determine linear dependence or independence, the same way that we had for vectors in Rn. Now, we had a result in Chapter 1 where we've got a similar result for vector spaces V. Any set which contains the 0 vector of a vector space is linearly dependent, because I could take as a linear combination any non-zero scalar times the 0 vector plus a linear combination of all of my other vectors where the weights are 0. So in short, any vector or any set containing the 0 vector must be linearly dependent. Now we have the following result, theorem 4.4, which is similar to a result that we had seen in Chapter 1, which says that an index set of vectors v1 through vp of elements in a vector space, which consists of two or more vectors, where the first vector, v1, is non-zero, is linearly dependent if and only if one of the vectors, v sub j, where j is greater than 1, is a linear combination of the preceding vectors, v1 through vj minus 1. So in short, if any one vector in our set can be written as a linear combination of the other vectors, then that set is linearly dependent. So now that we've introduced linear independence or dependence for sets of vectors in a vector space, let's look at some examples illustrating linear dependence or independence. So in our first example, we're going to work with this vector space of second-degree polynomials. And we're told to consider the polynomials p1, which is equal to 1, p2, which is t squared, and p3, which is 2 minus 3t squared. So we ask the question, well, is the set p1, p2, p3 linearly independent or dependent in P2, the space of second-order polynomials? And if this set is linearly dependent, we want a linear dependence relation among the vectors. So for this example, we can see pretty quickly that these vectors are linearly dependent. Because we can write the polynomial p3 of t as a linear combination of p1 and p2. In particular, we could take 2 times p1 of t minus 3 times p2 of t. And we see that this linear combination of the polynomials p1 and p2 would be equal to p3. So these vectors are linearly dependent, and a linear dependence relation among these vectors could be given by the equation that we've shown here, or if we want to rewrite this as a linear combination of vectors equaling the zero vector, we could say the zero vector is equal to 2 p1 of t minus 3 p2 of t minus p3 of t. So here our set is linearly dependent. So let's consider another example. In our next one, we are looking at the polynomials p1, which is equal to 1, p2, which is 1 minus t, and p3, which is 1 minus t quantity squared. And again, we ask whether the set p1, p2, p3 is linearly independent or dependent in the vector space p2. And if they are linearly dependent, we want a dependence relation among these vectors. So when we first look at these three polynomials, we may suspect that they are linearly independent. It doesn't look like any linear combination of two of these polynomials will result in the third. And indeed, these are linearly independent. Now, to justify our initial assumption, let's see if we can prove that these are indeed linearly independent. So if we were to consider a linear combination of these polynomials, that is something of the form c1 times p1 plus c2 times p2 plus c3 times p3, and set that equal to the zero vector, we want to show that the only constants that satisfy this would be the trivial solution. C1, C2, and C3 are 0. So let's write out this equation a little more explicitly. We have C1 times the polynomial P1, which is just equal to 1, plus C2 times the polynomial P2, which is 1 minus t, plus C3 times P3, which is 1 minus t quantity squared, or if we expand that, 1 minus 2t plus t squared. and we want to know when that will equal to the 0 polynomial, which would be identically 0. So expanding and grouping like terms, we have for our constant coefficient C1 plus C2 plus C3. For our coefficient of t, we have negative C2 minus 2 times C3. And for our t squared coefficient, we have C3 times t squared, which has to equal the 0 polynomial. Now, in order for this equation to be satisfied, well, our polynomial on the left-hand side must equal the 0 polynomial, which means all of our coefficients must be 0. So looking at the coefficient of t squared, we see that C3 must be 0. So if C3 is equal to 0, looking at our coefficient for t, we have C2 must also be 0. And if C2 and C3 are both 0, then looking at our constant coefficient, we're just left with C1, which must also be 0. So we find C1, C2, and C3 must be equal to 0. And so our set of polynomials P1, P2, P3 is linearly independent. Okay. So here, illustrating the definition of linear independence or dependence for a set of vectors in a general vector space. Now that we've defined linear dependence or independence of a set of vectors for a general vector space, we're ready to define what we're going to work with throughout the main part of this section, which is a basis for a vector space. So let's suppose that H is a subspace of some vector space V. So an indexed set of vectors, which is denoted as capital B, so let's say we have a set of vectors B1 through BP in the vector space V. This set would be referred to as a basis for the subspace H if two conditions are satisfied. The first condition is that B, this set of vectors, is linearly independent. And the second condition is that B is a spanning set for the subspace H. That is, H can be written as the span of the vectors B1 through BP. Now, the definition of a basis also applies to the case when H is equal to V, that is, if the subspace is the entire vector space, because any vector space is a subspace of itself. Therefore, a basis for an entire vector space would be a linearly independent set that spans the entire vector space. So let's look at some examples of bases for different vector spaces, and then we'll start studying bases in a little more detail. So in our first example, we'll consider a basis for our most familiar vector space Rn. So let's suppose that E1, E2 up through En are the vectors which are the columns of the n by n identity matrix. So these we've already worked with a little bit. If we have the n by n identity matrix E1 is the n-dimensional vector, which has 1 as its first entry and 0 as all other entries. E2 is the vector that has 1 as its second entry and 0 as all other entries. and so on up through En, which is the n-dimensional vector, which has 1 as its nth entry and zeros for all other entries. So the set consisting of these n vectors, E1 through En, is called the standard basis for Rn. Indeed, any vector x in Rn can be written as a linear combination of these vectors. We could take the first component of x times E1 plus the second component of x times E2, and so on up through the nth component of x times En, and we would get the vector x. We can do that for any such vector in Rn. So these bases are called the standard basis vectors for Rn. Now similarly, we can define a sort of standard basis for the set of 2x2 matrices with real entries. So if we think about the matrices where we have 1 for our top left entry, 0 for all other entries, or 1 for our top right entry, 0 for all others, or 1 for the bottom left or bottom right entry for 0 with zeros for all other entries, then this set of 2x2 matrices forms a basis for the set of all 2x2 matrices with real entries. Indeed, any 2x2 matrix with the general entries A, B, C, D can be written as a linear combination of those 4 2x2 matrices, where the weights A, B, C, and D are given as the entries in each of these components. Now, for the set of polynomials of degree n or less, the set 1 t squared up through t to the nth is referred to as the standard basis for that vector space. So indeed, any polynomial p of t that is of degree n or less can be written as follows. P of t would be some constant a naught plus a1 times t to the first plus a2 times t squared, and so on up through some coefficient an times t to the nth. So we see here this is just a linear combination of 1 t squared up through tn, which were the vectors in this set. So this set of vectors spans all of Pn, and these polynomials, 1, t squared, and so on, are clearly linearly independent, as no one of them can be written as a linear combination of the others. Now, if we're talking about the more general space of all polynomials, we would have an infinite set as our basis, consisting of 1 t to the first, t squared, t cubed, and so on, with t to the n being a general term. So here we've defined a basis as any linearly independent spanning set for a subspace or a vector space. Now, when we are talking about bases more generally, we can say if A is any invertible square matrix, then the columns of A must form a basis for Rn. Since they are linearly independent and the column vectors span all of Rn according to the invertible matrix theorem. So throughout this section, we'll keep in mind any square matrix which is invertible, and there's a number of ways that we can show a matrix is invertible, will have columns which form a basis for Rn. So we'll make use of that fact throughout this section and the remainder of chapter 4. So now that we've defined bases and we've seen some examples, let's look at an example problem where we're given a set of vectors and we have to determine whether it forms a basis for a given vector space. So in this first example, we are given some set of vectors, and we have to determine which of these sets form bases for R3. And in the event that we have a set which is not a basis for R3, we want to determine if our set is linearly independent or if our set spans Rn. And we need to justify our answers for each of these questions. So when we're checking whether a given set of vectors forms a basis, there's two conditions that we have to check for the definition. First, whether they are linearly independent, and second, whether they form a spanning set for our vector space or our subspace. In this case, we're considering all of R3 as our vector space. So in part A, we have three vectors. Let's call them maybe V1, V2, and V3. And we notice right away that this second vector is the zero vector in R3. So recall any vector or any set of vectors which contains the zero vector must be linearly dependent. So first, we can say that this set is linearly dependent since it contains the zero vector in R3. So as soon as we know that our set of vectors is linearly dependent, we know that they cannot form a basis for R3, because one of the conditions for a basis was that these vectors are linearly independent. Now, once we know that it does not form a basis, in this example we're asked, well, is the set linearly independent, which we've already established it is not. These vectors are dependent. And we're also asked to determine whether these vectors span Rn. So to determine whether this set of vectors spans all of Rn, we could consider a matrix, let's call it capital A, which has these vectors as its columns, 1, 0, 1, 0, 0, 0, and 0, 1, 0. And we want to see whether, well, one way we can see whether these vectors span all of Rn is by looking at this matrix in a row-reduced form to see if it contains a row of all zeros. So pretty quickly we can see by examining the first and third row of this matrix that they have identical, or that the first and third rows are identical. So if I take row 3 minus row 1, I would have the matrix in reduced row echelon form as follows. So we have a row of all zeros, which means that the set of vectors does not span all of R3. Now, another way we could have determined that is by looking at the determinant of this matrix A. Since we see its second column consists of all zeros, if we use a cofactor expansion down the second column, we see that the determinant of A is 0. So A is singular. That is not invertible. And by the invertible matrix theorem, as soon as we know that this matrix is not invertible, we know that its columns cannot be linearly independent, and these columns do not span all of R3. So in this case, we can say the set is also not a basis for R3. didn't satisfy either of the conditions to be a basis for R3. All right. So in part B, we have another collection of 3 vectors, and we need to determine whether this set forms a basis. So we want to know whether these vectors are linearly independent and whether they span all of R3. Now using the invertible matrix theorem, since these are 3 vectors of length 3, if we consider a matrix A, which has these vectors as its columns, if we can show that this matrix is invertible, then the invertible matrix theorem tells us that the columns of A are linearly independent and that the columns span all of R3. So therefore, these column vectors would be a basis for R3. So in order to show that this matrix A is invertible, well, there's a number of ways we could do it. One way would be to find the determinant of this matrix and show that it's non-zero. So here, considering the determinant of A by taking a cofactor expansion, let's say along the first row, because none of our entries are 0, it doesn't really matter which row or column we use, we would have 2 times the determinant of a 2 by 2 submatrix, which would be negative 12 minus 10. Then negative 1 times negative 8 minus 5 for the determinant of the 2 by 2 submatrix. And then minus 7 times negative 4 minus a negative 3 or plus 3 for the 2 by 2 subdeterminant. So let's see what we have. We would have 2 times negative 22 minus 1 times negative 13 or positive 13, and then minus 7 times a negative 1 would be plus 7. So we have negative 44 plus 20 leaves us negative 24, which is certainly non-zero. So we can say that A is invertible. And by the invertible matrix theorem, that means the columns of A span all of R3, and they are linearly independent. So the set of vectors which were given here forms a basis for R3. All right. Now in part C, we're given a set of 2 vectors in R3, and we need to show whether these form a basis. Now in this example, we can see clearly that these 2 vectors are not linearly dependent, since they are not scalar multiples of one another. So here, let's start by saying these are linearly independent, since our vectors are not scalar multiples of each other. So we've satisfied the first condition for a basis. Now the second condition is that this set of vectors would need to span all of R3. Now we can see here that we've only got 2 vectors, but we're looking at R3, and there's no way that a set of only 2 vectors could span all of 3-dimensional space. We know the span of a set of 2 vectors in R3 either defines a line or a plane in space, but does not define all of space. So here we can say the two vectors do not span R3. So the set of vectors we're given here is not a basis for R3. All right. Another way we could see that these vectors do not span all of R3 is to consider a matrix which has these vectors as its columns: 1, 2, -3, -4, -5, 6, and then row reduce this matrix. So we could take, for instance, row 2 minus twice row 1. So my first row will be 1, -4. My second row becomes 0, 3. And then I'm going to take row 3 plus 3 times row 1, which makes my third row 0. And then let's see, -12 plus 6 leaves me -6. And then I could take row 3 plus twice row 2, which gives me 1, -4, 0, 3, 0, 0. So as soon as we have a row of all zeros in this augmented matrix, we see that it cannot span all of R3. For instance, if we took some vector in R3 whose third component is non-zero, we wouldn't have a vector x which maps onto that vector in R3 with this coefficient matrix. All right. So in the next part of this section, we're going to introduce a result which we'll use in this section and throughout the remainder of Chapter 4, known as the Spanning Set Theorem. So what we'll end up seeing as a result from this Spanning Set Theorem is that a basis can be thought of as a sort of efficient spanning set which contains no unnecessary vectors. So it is like a minimal spanning set for a given vector space. And in fact, we can construct a basis from a spanning set of vectors by discarding any unneeded vectors from our spanning set. So as an example of that, which will illustrate what exactly the spanning set theorem says, let's consider the following. We will have three vectors, v1, v2, and v3 in R3, and it can be verified that v1 minus 3v2 plus 5v3 is equal to the 0 vector. So in other words, these three vectors are linearly dependent. There is some linear dependence relationship among these. So we're supposed to make use of that information to find a basis for H, which is the span of the set of vectors v1, v2, and v3. All right. So making use of the fact that there is a linear dependence relation among these vectors, let's see that if we can show that the span of these three vectors is a span of a subset of these two vectors. So to do that, I'll start by mentioning that every vector, let's call a general vector x, in H, which is the span of v1, v2, and v3, is of the form c1 times v1 plus c2 times v2 plus c3 times v3. Recall the span of a set of vectors is the set of all vectors which can be expressed as linear combinations of those vectors. So here any vector in the span of v1, v2, and v3 can be written in this way. But using the linear dependence relation, which was given in the problem, we see that the vector v1 can be written as 3v2 minus 5 times v3. Therefore, this vector x can be written as c1 times 3v2 minus 5v3 plus c2v2 plus c3v3. So since v1 can be written as a linear combination of v2 and v3, the vector x is now a linear combination of just the vectors v2 and v3. To see that a little more clearly, if we group these terms together, we have a coefficient of 3c1 plus c2 for the vector v2, and a coefficient of negative 5c1 plus c3 for the vector v3. So as I mentioned, x we have shown can be written as a linear combination of just the vectors v2 and v3. Therefore, the vector x is an element of the span of the vectors v2 and v3. All right. Therefore, so we've shown every vector in the span of v1, v2, and v3, which was h, is also in the span of just v2 and v3. Now, that means that the set H is the span of v2 and v3, since every vector in that set can be written as a linear combination of v2 and v3. So H is a spanning set of v1 and v2, and if we can show that v1 and v2 and v3 are linearly independent, then we've shown that they form a basis for H. Now I'll say here clearly the vectors v2 and v3 are linearly independent since they are not scalar multiples. So recall for a set of two vectors, they are linearly dependent only if one is a scalar multiple of the other, which clearly the vectors v2 and v3 are not by looking at maybe the second component. To get from 1 to 0, I would have to multiply v2 by 0, and we see that we would not get the vector v3. So since they're not scalar multiples, they are linearly independent, and they span the set H. Therefore, the set of vectors v2, v3 form a basis for R3. All right. So this example, or the work that we've done in this example, can be generalized, and we get a result which is known as the Spanning Set Theorem, which says if we have a set of vectors S, which are vectors v1 through vp, and this is some set in the vector space V, and we define H to be the spanning set of that set of vectors v1 through vp, then in part A of this theorem, if any one of the vectors in S, let's say for instance vk, is a linear combination of the remaining vectors in that set, then the set formed from S by removing the vector vk will still span all of H. So as we've seen in this previous example, if we were able to write v1 in terms of v2 and v3, then the set of vectors just v2 and v3 still spans all of H, since v1 was a linear combination of the others. So that holds generally. And part 2 of this theorem says if H is not the subspace consisting of only the zero vector, that is the zero subspace or the trivial subspace, then some subset of the collection of vectors S is a basis for H.